Hello, and welcome back to Our Future in Space, where we delve into topics related to human civilization as we move out into the solar system. I'm your host, Dr. Jeff Greenblatt, Vice President for Science and Research at Orbital Assembly Corporation, and I'm joined in the studio by Eric Ward, who is the Vice President of Engineering Design at OAC. Hey, Eric, how's it going?
Hey, it's going very well, thank you. Yeah, I'm really excited. We've got Dr. Martinelvis here to talk to today. He's an astrophysicist at the Harvard-Smithsonian Center for Astrophysics. And among other accomplishments, he has published over 400 papers on quasars. He is the author of Asteroids, How Love and Fear and Greed Will Determine Our Future in Space, and has asteroid 9273 Martinelvis named after him. So interestingly, Jeff got this interview set up and didn't realize that Martin and I already knew each other. He and I actually co-founded a company some years ago called Atom Engineering that did asteroid prospecting.
Yeah. So, well, yeah, it was a big surprise for me as well. And so, Martin, I guess you've been involved with asteroids for a long time, but it isn't what you've spent your whole career on. Maybe you can tell us a little bit about how you got from where you started to your current interest.
Sure, yeah. My career has been very much involved with space astronomy as I tried to understand how quasars work. These are supermassive black holes at the centers of galaxies that emit more light than the whole galaxy sometimes. And that led me from starting with the discovery of X-rays from them, which was my thesis. Then we went on to look in other wavelengths, and they kept showing up all over the place, the whole spectrum. So you need a large number of telescopes working at many different frequencies to really understand quasars. And it turns out that that was like the forerunner of how modern astronomy works. It's very hard to do real astronomy nowadays in the 21st century without using all the different wavelengths that come to us from these objects. That's how I got into quasars and things. The step going to asteroids was one based on my fear that the good days were over, the good times were over for astronomy, because we just couldn't afford 3 James Webb Space Telescopes at once. And so we'd be able to study the optical and then wait 10 years, get older, and study the infrared, wait 10 years, get older, study the X-rays, and that's no way to do science. So we had to bring down the cost. And my happy thought was, that's one thing capitalism is really good at, bringing the prices down, right? So if you have competition and innovation, you can bring the prices down a lot. Now, this was before Elon Musk and SpaceX really already started that process. But I think the ultimate cost reductions will come, and capability enhancement of what we can do in space will come when we need the resources of space. And that means at the moment, that means the moon and Mars and the asteroids. And I know nothing about the moon, or I certainly did know nothing about the moon. I've learned a little bit now. But asteroids look like stars. That's what their name means, right? It means sort of not really a star, but it sure looks like it. So I could use all the techniques of astronomy that I'd learned studying quasars, which are also almost stars. The names mean the same thing. And to bring them to bear on asteroids. And so that seemed like a hopeful path. And so I've got into that ever since. How do we make space resources, particularly asteroid resources, into something that we can sell, and thereby bring down the price of access to space and doing things in space for astronomy and many other sciences.
Yeah, and so I mean, just to step back for a second and ask, so why, in your view, is it important for us to start going out to the asteroids and, prospecting, perhaps mining, bringing materials back to Earth system? I mean, what's the context here as you see it?
My book has the subtitle Love, Fear, and Greed. And bringing materials back, it's about greed. It's about making profits. And there's nothing wrong with that. So I do think there's probably going to be need for regulation. There's going to be need for legal lawyers in space, basically. Nobody likes the idea especially freedom-loving people who want to go out into space and be very independent, but they really won't like it if there aren't any laws that work there.
Right.
Simply just getting mineral rights, for instance, is crucial to getting a mining industry going, both moon and any space resource, but moon and asteroids. But I have no problem with profit being the motive, because it will, and that the end of my book is all about how by bringing that cost down, we will also enable in much more exploration of the universe, which is what I mean by love of knowledge. And we'll also remove the threat from asteroids that might come and wipe us out, or even just wipe out a mere metropolitan area. Right? That would just, we can stop that. We know how to do it in principle. We don't have the real capability yet at anything like an affordable cost.
Right. I mean, we haven't made the investments in that technology other than a few R&D projects, I guess. Yeah. We have demonstrated that we can nudge an asteroid, but I mean, maybe you can tell, I know a lot about this and I'm pretty sure Eric does as well, but maybe you can tell for our more general listeners, what is the threat of asteroids? Why should we worry about them possibly impacting the planet? And how often might that threat be realized if we do nothing?
Well, the reason to worry is they do hit the Earth, and there's probably one a year that's big enough to take notice of and would hit the Earth. But that wouldn't cause much damage. Once every 20 to 50 years, it's pretty undetermined. There's something that's like the impact on Chelyabinsk, which might actually hit the ground, and so if it came in at a slightly steeper angle than that one did, that would be bad news for anyone underneath. That's the kind of thing that would destroy a metropolitan area, and that's only 20 meters across. That kind of diameter. That's pretty small still. So these will happen, and we need to be able to find all these and move them out of the way.
And you really think that's? Yeah, go ahead, Eric.
I was going to ask.
The dinosaur killers are very rare. We found 90% of them. But that's not enough. We need to find 100%, and so there are plans afoot to find the rest of them.
So how do we find them? How do we locate these asteroids? How do we know if they're going to be potentially hazardous?
Right, you have to look at the whole, as much of the sky as you can, as deep as you can, many times, so that you can see a little point of light moving. And that has, at the moment, you basically got ground-based telescopes that are doing this, like the Atlas system in Hawaii, and Catalina in Arizona, and the Zwicky Transient Factory in Southern California. There are these efforts going on. They're limited because they don't always go deep enough to find all the ones we want. They don't go deep. Many of the asteroids we care about are actually very dark. They reflect less light than that blackboard behind me. And so they're very faint. So a good way to find those instead is to look in the infrared, where they're glowing with the heat of their temperature, appropriate temperature, and that turns out to be around 5 to 10 microns. And so Amy Mainzer, now at the University of Arizona, formerly JPL, has been developing a mission which is now called Near Earth Object Surveyor. And NASA is finally building this, or they're getting close to building it. They've gone through their Phase B review, which as it's called. So I think that's going to fly 2027, and it will. Ooh, yeah, there you go. Nice picture. That's the earlier version, but it looks pretty much the same, I believe, now.
And does this have to be space-based at these wavelengths?
Yes, because what we're looking for is something the same temperature as the Earth, same temperature as the sky, and so you've got an enormously bright background. So doing it from the Earth is really hard. Also, if you do it from space, it's easier to look close to the sun, and because you don't get scattering from an atmosphere, and that means you can see things that are kind of hiding with very long synodic periods. That is the period between appearances close to the Earth, and that's probably where the last 100 really dinosaur killer class asteroids are lying. So they very carefully designed it to look close to the sun as well.
And would a single mission like the NEAS that you're talking about essentially find all of the dangerous asteroids, or would we need a complement of,
Yeah,
instruments in different orbits or different wavelengths?
it's pretty darn good.
Your-
It finds the big ones, like bigger than 140 meters in diameter, at like 90% of them, or something like that, 90-something percent. Working in combination with a ground-based telescope, a really big one that's coming along called the Vera Rubin Observatory, which is going to start next year probably. It's been delayed by COVID. Working on what's called the Legacy Survey of Space and Time, and that's basically taking pictures of the whole sky accessible to that telescope from its mountaintop in Chile. Every day, every night, many times for 10 years, and it's a big telescope, an 8-meter telescope, so it collects a lot of light, and so it can go fainter, and will pick up some of those very dark asteroids that would otherwise escape. And then you combine the two, and you get an even bigger fraction.
Right.
And best of all, from a prospecting point of view, if you're interested in the resources, but also because you want to know how to deal with the threat, you want to know what kind of asteroid you're looking at. The combination of the optical reflected light with the infrared light tells you how dark the asteroid is. And if it's very dark, then it's almost certainly a very carbonaceous rich asteroid. And if it's very bright, it's probably, it could be a metallic asteroid. It could also be just made of ordinary silicate rock. And those are the three possibilities.
So tell us a little bit about that. You mentioned asteroid prospecting, which we are interested in. Obviously, a passion of mine, but, as we're talking about, the future of humanity in space and, not just the capitalism, but the resources you're going to need to support a civilization, asteroid mining is thought to, going to become a big part of that. So tell us a little about the prospecting side of that. I think that's a pretty astronomy focused side of that actual mining industry.
Yeah, I keep arguing with folks that want to do mining that the first thing you do is survey the sky with astronomical telescopes, because it's so much cheaper than sending out many missions to individual asteroids and trying to assay them there, because 85% of them are going to be just stony asteroids which aren't particularly rich in any resource. Whereas if you can isolate the carbonaceous ones, some of which are very rich in water, some of which are not, which is something we now know, by the way, because the two probes that are bringing back samples, Hayabusa 2 and OSIRIS-REx, they're two asteroids who are very different. The Ryugu is very dry, and instead Bennu is really water rich. So, and they didn't know in advance. No one knew.
And they're both carbonaceous asteroids.
They look essentially the same from astronomical spectra. So, what astronomical spectra do? This is a picture of Bennu from OSIRIS-REx. What the astronomy does is narrow it down. So instead of looking at 100% of the asteroids, you only have to look at a few percent, 5%, 10%, something like that. And you cut the number of exploratory missions by a factor of 10, and that makes it more plausible that you can make a profit on the enterprise. So I think that's good.
Yeah, I would imagine before you send. I'm sorry, Eric.
Go ahead, Jeff. Yeah.
Before you send a multi-$100-million spacecraft, I'm assuming, to an asteroid, you better be pretty sure it's worth it, right? Yeah. In other words, that there's going to be something of value, or at least that you are narrowing the range where you know for sure that there's at least something valuable, and maybe it would be even more so. Can you address that a little bit?
When you get to a few $100 million, you're going to have one. Right? And that's going to be a real miner to actually extract ore at some level, right? The next phase, the phase in between astronomy and mining, is probably small sats, large CubeSats that go out and maybe cost $1 million each, and they can do some assaying on site and tell you exactly how rich the asteroid is. And it has to be at the $1 million kind of level, because you're probably going to mine $1 billion worth of ore from a good asteroid, a good candidate. And so you don't want your exploration costs to be a very big fraction of that. and you may have to send out 10 to find one.
Right.
It's going to be in the $1 million range, not in the 10 or $100 million range.
Yeah, that makes sense. I mean, there's also a lot of asteroids out there. I mean, give us a sense of the count here. We're not talking about a couple dozen orbiting or near the Earth, right?
Near the Earth is of order 100,000, bigger than some reasonable diameter. No, I have to correct myself. The number bigger than 100 meters in diameter is only about 20,000. There are many more smaller ones.
Right.
Of course, those are a tiny fraction of the total population of asteroids. If we can get out to the main belt, then there are millions upon millions, and some of them are extremely large. So that would be what the bonanza would be, finding one of those that's really big, several kilometers across, and rich in what you want to mine, and then you can keep going back to the same one, and that probably is an efficient way of working.
For some of the biggest asteroids like Ceres and Vesta, the ones that were discovered centuries ago, right? Don't we already have a pretty good idea from the measured spectra of what their composition is, and why don't we just mine those? I mean,
well, certainly Ceres and Vesta have been visited, right, by the Dawn spacecraft, so we have a much better idea in that case. Ceres has got a huge amount of water inside it, we believe. I think it's about 1/5 of the volume of the oceans on Earth.
Wow, that's immense.
Yeah, pretty immense. Yeah. I think there's a problem there. Ceres is a unique object. It seems to be a planetesimal left over from the original. It may be the only one we can find, or it may have come from the outer solar system, and those two needn't be mutually exclusive. There's some case for turning that into some kind of national park, solar system park. And the same would apply to some, the biggest and fanciest of, or most special of all the asteroids. So I'm a bit worried that there are going to be cases where greed and love of knowledge collide, right? This is where you start talking about. I think for quite a long time we won't have to worry. There are plenty of slightly smaller ones that will provide an enormous amount of resources compared with what we're used to using.
So what are these resources?
Sorry? Oh, yes. We have.
Yeah.
Essentially, there've usually been two things talked about. There's a squeaking noise coming from somewhere. There's platinum group metals, which are particularly rich in the metallic asteroids, in some of the metallic asteroids. And they could be worth $50 million a ton. That's great. They have the downside, and you can sell them on Earth. There's no doubt about that.
Yeah.
I even talked to an economist who reckons it's a fairly elastic situation, so the price will not come down. The demand is elastic.
Yeah.
So that's good. The bad news is that a ton of raw asteroid nickel iron, which is what it is, metallic asteroid, it contains a few, like 30 grams of platinum group metals. So a couple of ounces, a handful.
And it's not all in one place. You have to essentially distill the asteroid.
Yeah.
Right? The metal from it. Yeah.
And of course, because of the rocket equation, which we can talk about if you like, you don't want to transport dead mass anywhere in the solar system. It's really bad news. It'll put you out of business. So you have to refine these platinum group metals out in the native orbit of the asteroid. And so that's a demanding job that I don't think anyone has really tackled seriously. And I would love to be proven wrong about that, but I haven't seen anything yet.
Yeah, I mean, what you're describing is a very large-scale space mining operation where, in order to get substantial amounts, I'm guessing hundreds of kilograms or whatever the market can bear of, say, platinum group metals, which is platinum, palladium, iridium, and a few others. Can't remember them all. You essentially have to mine many hundreds of tons of, thousands of tons of material. And so you can't bring it back to Earth and do it there. So you essentially have to have a full mining and what would you call that
refining?
Process? Refining operation in space. with
Yep.
power and probably people or robotically operated.
People are tough.
Very-
People would be tough to do because of the radiation. You're going to stay out there for a couple of years. One of these synodic periods is a small one, is a couple of years, because there's no opportunity to get back otherwise, and that could very easily be deadly. So unless we solve that problem, it's got to be robotic.
So we talked about platinum group metals, and
Yeah.
I'm sure there are some other resources that you might want to tell us about.
Right. Two. There are two. The other one that people talk about a lot is water, and that now is completely different. You don't bring it back to Earth; you sell it in orbit.
Yeah.
Because it costs at the moment $3,000 a liter for water to bring it up to space, even low Earth orbit. Double that to go to a higher orbit, and so it's reasonable to think you might be able to undercut that by all water brought from an asteroid. Energetically, no problem. Financially, not obvious, and that's going to be that's a moving target. Depends on how, as we get better, cheaper launchers, that will make it easier to supply this water from the ground. On the other hand, it also makes it cheaper to go mine it from an asteroid or from the moon.
Right.
So that's a complicated economic question, and people are going to have to just try it and see, I think.
And the demand for water in space is pretty high because it's more than just drinking. It is also rocket fuel.
In principle, it's great. You can use it for life support, drinking, hygiene, and rocket fuel. But at the moment, there is no market, right? The ISS is all there is, and they use one ton per astronaut per year. And that's because they live in not very pleasant conditions. My bet, and I have a whole chapter in my book on this, just happenstance, there is that the market's going to grow very rapidly. Axiom and Orbital Reef and these other excellent in-space space stations, the first generation of them are coming along right now, right? I'm sure you guys will be providing the second generation of them, and that will be even better.
Perhaps even first generation.
Well, good for you. Yeah. Axiom does have a contract with for NASA. Give them a slight edge. Orbital Reef doesn't, I don't think. So you could compete with them very clearly.
But the point is that we have probably dozens of people soon to be living in space, and hope that will grow to hundreds, and then there will be a substantial market for water and other life support.
Exactly, and I people who go up who are not tough astronauts will want a shower and a toilet that works and so on. The water supply will be needed, will be much bigger per person, as well as there being more people. So I think it's going to be a significant market on the time scale of 10 years, something like that. 5 years, there will already be quite a lot more people in orbit, I believe, if Axiom really goes ahead. And then we're going to build up pretty rapidly from there. And so it's the in-space demand that has to come first. And then that will, it will stimulate the production of resources from space. Or, of course, a clever capitalist will get in first at just the right moment to be there with the bag of water ready to
right.
Good luck to them.
Sell it at 10% less than you can get it from Earth, so therefore they get the market share.
Exactly. Yes.
Yeah.
And it'll be never gone through any biological creature before, so you couldn't be purer, right?
Yes, that's right. Eric, I think you're asking. There's a third category.
He mentioned the third that he hasn't talked about yet. Exactly.
And that's because I was very stupid and didn't think about it. But again, the same demand. There will also be a big demand for construction material in space, because if you can supply your basic iron girders for building big space stations such as your own, where you have 1 G to worry about, or maybe a third of a G. You've got to have strong material to support that, and you'd much rather bring that material from an asteroid than from the Earth. And so I think the iron of those, when we said we pick up 30 grams of platinum group metals, that's coming out of basically pure iron. So that's the easiest thing to cut. You just cut it and move it. However much
you don't even have to do anything. You're saying it's already a strong alloy.
Yeah, so we believe. Yes. What we don't know is if it's a single solid block or if it's mixed in with other rock. And I think the recent studies of Psyche in preparation for the mission Psyche, so 16 Psyche is the asteroid that's probably the biggest metallic asteroid in the solar system. That it may not be pure metal. It may be mixed with other things. So we'll find out on that mission what other one of these looks like.
But even if it were mixed with rock bits, if it's still substantially, if more than half the weight, let's say, is iron and nickel, that's not very hard to just extract that, melt it. You can separate out the rocky bits fairly easily, and then you've got a steel building material, as you say, that can be used for all kinds of space construction.
Yeah.
But what's interesting, when you first mentioned this, when we were talking last week about this interview, and you said there's going to be lots of iron for construction. And what I thought is, iron is very commonly used, of course, on Earth. It's cheap, it's plentiful, it's strong, but it's also pretty dense. And for space-based construction, we almost always build our spacecraft out of aluminum or even carbon fiber, or exotic alloys that try to squeeze every last gram out of a structure. So, are we going back to an iron-based construction economy as we move further out into the solar system?
Well, because you only do all that complicated high-tech stuff because of the cost of getting things to orbit. And the old Russian spacecraft didn't do that, right? They just had bigger rockets and they sent up wooden tables and so on. And this is
really? I didn't know that.
Oh yeah. Yes, if you can. So you're not the price advantage. It now occurs to me is even better. You're not competing with iron from the ground. You're competing with high-tech titanium alloys and stuff. So you can actually come in at quite a high iron price.
Right. It's still cheaper than the alternative.
The high-tech materials. That's a nice trick.
Yeah. I love it. It kind of puts an extra gloss on the idea of steampunk,
Yes,
sort of return to
love it.
Iron. Yeah.
Yeah. I saw a few years ago a proposal for a spacecraft that mined water from asteroids. And it would use that water, just heat the water and use it as propellant to get back to Earth. And so there we get a steam-powered spacecraft out of the deal too. So,
right,
excellent.
Yeah, very good. So maybe so you mentioned something a few minutes ago that I wanted to touch back on an appropriate time. So maybe now is the time. When we were talking about large, perhaps you didn't use this word, but I'm going to, charismatic objects like Ceres or Vesta or other kind of unique objects in the asteroid belt, or perhaps unique moons, our moon, some of the moons of Jupiter and the other outer planets. And you said maybe we want to leave those alone. Maybe you can tell us a little bit more about why you think that and about the paper where I first discovered this idea that you had written with a colleague. I'm going to bring it up now just to remind people.
An ethicist from King's College London, Tony Milligan. There we go. How much of the solar system should we leave as wilderness? Well, this was really an economics argument about exponential growth at first. Basically, if you extrapolate our use of iron from the 1800 when the Industrial Revolution started to 2000, it grows at 3.5% a year. Pretty consistently, and although I'd love to have better numbers for the old production rates, but it's good enough. If you extrapolate that forward, how long before we use up all the iron in the asteroid belt? Remembering that we're looking very far in the future then. Yeah, right? Ridiculously far. Yeah, except it isn't. Because of exponential growth, right? It's 10 million times the resources we have on reserves of iron we have on Earth, but it still becomes a small number when you allow for the doubling time of 20 years. The answer is it takes you at 3.5% growth, which is what we've experienced so far. It takes you 350 years to exploit 1/8 of it. It then takes you 60 years to eat up the remaining 7/8. It's all gone in a long time. right?
Right.
Now, if some space enthusiasts think this will grow at 10% a year, be a real gold mine, then
Sure.
basically cut those numbers in half.
Hmm.
So we start to run into, we won't feel like it, but we will actually be close to exhaustion of those resources in 150 years or 200 years, something like that, which is not long.
Yeah, and I think what really struck me when I first read this paper was, we better learn our lesson from the Industrial Revolution that unbridled exponential growth still has limits, even if you're now thinking on the scale of the solar system. Right. And we ought to apply some. We don't want to tamp down growth, but we have to have some natural limits. Otherwise, we not only run out and then have a crisis, a material or energy crisis, but we also have consumed all the things that we consider precious and unique about where we live, right?
Absolutely. One of the numbers that I think I got after that paper is if you want to terraform Mars and eventually get to blue Mars, where you've filled this northern ocean, the amount of water you need to do that is almost exactly the same as the amount of water in Saturn's rings. So obviously, we just take away Saturn's rings and fill Mars's ocean.
Obviously.
And so I can't see anything wrong with that. Can you?
Yeah, I mean, I can see that the space environmentalists or whatever they're going to call themselves are going to be like shouting and hooting well before, the first time this is ever proposed, because, yeah, I mean, plus there's other sources of water, right? I mean, I think you're.
Oh, yeah. I mean, you wouldn't actually do that. You'd take Ceres first.
And you probably don't even need to destroy Ceres because there's even more water elsewhere in the outer solar system.
Yeah. I haven't calculated that. So I won't.
Yeah, maybe most of it's there. But
yeah, Jeff, I recall you having done an analysis on the amount of water in the solar system at some point a while ago.
Well, I mean, there is just so much water once you get past what's called the frost line, which I believe is somewhere between Mars and Jupiter, right? It's in the asteroid belt.
Yeah.
And then from there on out, you have objects that have frozen water, as well as carbon dioxide, nitrogen, and other things that are gases here. That unless they've moved close to the sun in billions of years ago, they're still frozen, and so there is an enormous amount. They're harder to get to because they're much further away, right, from us than say Ceres is. But I don't have the numbers at the tip of my
that's absolutely correct. The comets and many Kuiper belt objects are probably largely ice.
Right.
So it's not surprising, really, because hydrogen and oxygen are two of the most abundant elements in the universe. So it's not too surprising. But the problem with economically doing that is that the transit time is very long to the outer solar system with current rockets. So you would need to at least get fusion-powered rockets or something like that to make this economically attractive, which is not completely crazy. There are at least two teams trying to build fusion rockets, very different concepts. Maybe they'll succeed.
Do you want to tell us a little bit about fusion rockets since you're on the topic, or?
Well, fusion reactions, of course, give you a lot more power per gram of fuel. So you beat the rocket equations a lot, and the exhaust velocities can be very high. So you get a lot of specific impulse, and that's good. So you can go much more quickly from around the solar system. There was a study by, what's it called? Princeton Satellite Systems, I think they call themselves, looking at, with a particular design that they're trying to push, they could do a mission to Pluto, and it would take, get it right, I think it would still take like 5 or 10 years to get there, but just New Horizons took longer and was moving at a huge rate of knots as it went by. This would be able to stop and go into orbit around Pluto, which obviously tells you almost a lot more. So the amount of power you have is kind of ludicrous compared with what we have now.
Ludicrous speed.
Yes, ludicrous. Right. Where did I hear that before?
No, somebody I've met, I think.
He's some loser. He's never going to get anywhere.
So I actually am familiar with that study, and yeah,
Oh,
that was
yes.
really interesting. It's a kind of fusion, deuterium helium-3 fusion,
Right.
which is harder to achieve compared to the kinds of fusion that are being tried in Earth laboratories right now. But it has an interesting tie-in to space resources because of that helium-3, which
That's true.
is plentiful, we think, in the lunar regolith, embedded in the surface from the sun, but also elsewhere in the solar system. Do you want to?
Embedded in the surface of the moon.
The moon.
Right,
Yeah.
surface of the moon, but also in the gas giants in the
Mhm.
outer solar system. There's a lot of helium, 3 mixed in with the regular
Also,
helium and hydrogen.
there should be in asteroids because it's a bare rock surface that's been illuminated by the sun a lot, especially if the ones
Right.
that go closer to the sun. So that
Mhm.
might be, but then it won't be so obvious because the gardening effect where asteroids bang together and they do this and come back down, so that the outside becomes the inside. You will hide. It won't just build up and up and up on the surface. It will be more distributed through the asteroid. I would think.
So more like having to dig for platinum. You sort of have to mine the whole asteroid to
Yeah,
get the small
yeah.
amount of.
So better be useful. I'm not. There's certainly reasons to doubt that that the moon is going to be a valuable source for helium-3. The energy you need to extract the helium-3 is probably more than, and take it back to Earth if that's what you want to do. Probably more than the energy you got out of the reaction.
But if you're using it for space propulsion, it might be a different story. But it boils down to how hard it is to get.
Yes, and of course, the place where you're going to pick up that helium-3 from the moon are the big lunar maria, which you can see from Earth, and you're going to strip mine those on a large scale, hundreds of kilometers, and so it will be visible permanently from Earth what you did there. So that runs into the should this be wilderness or not problem.
Yeah, I mean, this idea of space wilderness is a really, I think, important topic to be elevating to public discussion because nobody's really thinking about it right now because we're not really in space or doing anything on a large scale. But it's my feeling that we better kind of get our policies lined up before that starts, or it might be too late to stop.
Yeah, especially if they get to be vested interests, and there are people, making billions or more out of some particular thing that we would say, we really don't want you to do that. It's not like, so when there are vested interests, it's best to try to avoid those. It's best to get in quick while you can. This is what's called acting from behind a veil of ignorance, which is a term that Rawls, a philosopher, invented to describe a situation where you don't know what role you're going to play in society, or whether you're going to benefit or lose from a particular set of rules. So when you set up those rules, you'll be careful to make sure that nobody gets completely thrown by the wayside.
I see. So it remains something where everyone has some stake and some influence in the final outcome.
Because you aren't sure how you're going to win or not. You're not sure how the outcome's going to be for you. And so that he called that a great way to find a good, a just system. It's a very clever idea, much talked about in philosophy circles.
Yeah, it's interesting how a lot of these, kind of philosophical questions that are just theoretical, as we go out into space and change our civilization that way, some of them will become very, very real very quickly.
Just like the trolley problem was amusingly abstract until we had self-driving cars, and then it suddenly became very real.
Yeah. So you talked about you talked about your 1/8 principle. So what is that, and why is it useful?
Well, that's because if you've consumed 1/8 of your resources, then you're only 3 doubling times away from consuming all of them. And the doubling time is pretty short, and we're talking about an economy that is many, many times bigger than our present world economy. So it's going to be very tough to change that. So we thought 1/8 was actually, we'd like to have made it smaller because you really need more time. But the problem with, as we know from COVID and so on, projecting how exponential growth will go ahead can be very uncertain. A small change in how doubling time will make a big difference in when you hit your problem. And
So
we didn't want to propose something that would not be practical.
right, like if you said if you consume more than 1/100th, you have to stop. That might just be seen as overly conservative. But
because your growth rate may not be 3.5%, and your doubling time might be 50 years, and you know, I wonder what number would be actually acceptable. Oh, it'll last 1,000 years, fine. You know.
Well, it's a really interesting larger question of if we ever get to the point where we are consuming that amount of resource and we're not destroying indigenous, land or extant species that are in danger of being, extinguished, or charismatic objects in the solar system, like it's all sort of available. And of course, there's going to be people who don't want to mine any of it simply because they want to keep things exactly how they are for scientific value, or maybe just because we don't think it's our place. But there's a balance point. I guess the point I'm trying to make is no matter what sorts of constraints we place, we might run into this situation where we've basically mined everything that we can realistically.
Yep.
And then what? Are we at a stagnant economy like people are starting to imagine we might be heading toward here on Earth? Or
people talk about a circular economy. Remember, it's no longer true that that economic growth requires more energy, right? The amount of energy we produce does stop tracking economic growth some years ago. So they can have economic growth without having material use growth at some point, at some level. So we would have to emphasize different things.
Right.
Right.
Right. But there is a certain amount of material that gets degraded to the point where you have to obtain new material to replace it. And that's especially hard in space where things get scattered and you really can't recover them.
Yeah.
Right? Rocket exhaust, for example.
Exactly.
For instance,
yeah. Right. Yeah. It's gone. Sorry.
Mm-hmm.
And the other thing is, an economy this big is presumably serving a much larger population. And where are those people going to live? Well, in O'Neill cylinders, basically. There's not enough room on Mars or even Venus if you could terraform either of them. It's that you can cope with a population maybe 4 times the size of Earth's population at the same density. But anything beyond that, sorry guys, you've got to live in artificial space cities. And you can't recycle somebody's home like that. Well, you can, but
but if you build these larger O'Neill cylinders, that actually then makes it easier to recycle materials within them, I think, because you're not losing them to space, but they're contained within an atmosphere and a gravity level artificial, and you can reprocess and reuse much more efficiently, I think.
All that's good, yes. But it's surprising what calculation I just did. I'm trying to remember it accurately. The space station is recycling at something like, oh gosh, I really ought to look these numbers up, 90-something%. But that still means that they lose a lot over, say, 5 years. You've lost a good fraction of the water, and you have to replenish it. And I did it. I said, oh well, these cities could be 99% good, and it lengthens it, but you're still looking at losing, I think, half your water in 50 years. And 50 years is nothing if it's a city, right?
Yeah. Right. Yeah, we're looking at permanent structures that would be hundreds of years old, being maintained in space, just like the cities here on Earth.
Right.
And so you need a long-term solution for that.
And it's not very easy because you're not building on solid rock. It's the basic structure is something people built, and it will break, right? Because things break at some point. And how you engineer for a 1,000-year lifetime is an interesting question.
It sure is. I think that might be a good topic for a future call.
There's this thing, mean time to failure, right? Which I'm sure you're familiar with. And if you have a lifetime in mind, to get a 99% chance of lasting that long, you have to build it for 5 times that long. Build it to specs that should last where
Yeah.
the mean time to failure, which is 5 times as long. So if you wanted a 1,000-year city, you have to spec it to 5,000 years, which is getting challenging. That's pyramid type.
Yeah, I don't, right. And they only exist because of the sheer bulk of material, I would say.
Right,
I mean,
and
good
they're not in good
engineering
shape.
too, but
They're not in good shape.
Yeah.
no, they're not. That's right.
Do you know the Clock of the Long Now? Danny Hillis's project in
Yes.
It's a 10,000-year clock. It's designed to keep good time for 10,000 years. It doesn't do much. It ticks every so often, like every year or something.
Yeah.
But
right.
It's an interesting first exercise in how could you build something long enough lived to
support a civilization like that.
Yeah, right.
Yeah.
So yeah, I mean, this is part of what we're trying to do is long-term thinking, you know, beyond just looking at the next election cycle or the next wave of consumer demand. So
or the next fiscal year, but really looking to, you know, how a civilization might support itself, you know, as a whole. So
determine these long-term goals, but then you have to actually worry about your next quarter at some point.
Yeah, for sure.
Sure, that's right.
So we're getting kind of short on time here, but we have some questions that we wanted to talk about. Maybe you could address Aidan kind of on this topic of these long duration projects and thinking about how, you know, we might get to a point where we're in, you know, hundreds of years running out of resources in our solar system. Have you thought about, you know, how that might push us to colonize other solar systems and what that might look like?
A little. Let me think. You would suppose you could do it, and we had magical 23rd century science that allows us to instantly go from one star system to another. Greg Egan, in his book, what was it called? I think it's Diaspora, says that conquering the galaxy is something that bacteria with spaceships would do. Meaning it's an incredibly primitive idea. Come on, guys, you've got to get over that. And so I hope we again realize that these exponential growth systems always lead you into a catastrophe at some point. And maybe it's the galaxy, maybe it's the solar system. If you just want to expand beyond the asteroid belt, then you could go to the Kuiper belt outside the orbit of Neptune. And there are some big dwarf planets there, of which Pluto is the prime example. And they would be full of they have 10 times the resources or 10 times the mass of the asteroid belt. And so that you think, oh, well, that's great. But remember, exponential growth, factor of 10 is 3 and a bit doubling time. It doesn't buy you very much. And then you have to get the Oort cloud where all the comets are, and they're mostly ice and dirt, and there's nothing much to them that's probably very interesting. But that would be many more, a good number more doubling times. But now your transit times like up into decades, even with fusion rockets. So,
sure, and you're consuming a lot more resources to accelerate the transport if you're going to be.
Yeah, there probably is some point at which it's simply the curves cross and you don't win at all, right?
Right.
Yeah. And I don't know about going to other star systems. That I think basically totally depends on new physics that we don't have yet. So there's some fun ideas. Planet 9, which is hypothesized to have kicked some of these dwarf planets of the Kuiper belt out of it into weird elliptical orbits. One idea is that it's not a rogue planet captured by the solar system, but a small black hole. It would actually be baseball size, this big, right? And that would be very exciting because we currently have very little. We can't do any experiments on black holes. We can watch them do things in space, but if we could go and experiment with them, we could see if they really are as simple as we think. Right? They're supposed to just have mass, spin, and electric charge, and in practice, no electric charge because the universe would the gas around them would neutralize that. So that's it. Complete description of them. That may not be true. when we actually come face to face with one. So experimenting with a black hole does sound kind of dangerous, but at least it would be in the outermost part of the solar system where
That's right.
the safest.
Not going to suddenly slide toward Earth.
No,
Because
it's
that's
not
not
going to
how
whoa!
right.
Yeah.
Yeah, no, that would be tremendous. An up close black hole that we could study at our leisure. Sort of. I mean, you're still talking about hundreds of astronomical units away, but that's comparatively close.
100, something like that.
That would be
I
fascinating.
think the odds are still in favor of a rogue planet because we know there are those, and we don't know that there are these baseball-sized 5 Earth mass black holes, but it still could be. So
yeah, well, that love of science and knowledge really makes me hope that it's a black hole.
Yes, indeed, absolutely. Me too.
Yeah.
How did you guess?
Yeah, big one.
So we've got one more question. I think we got time for one more. So what about geologists? I know you're working with asteroids, and I know people have called that planetary science. Do you work often with geologists, and and how do these fields overlap?
The people who work on meteorites tend to be geologists, and but there are very few people who actually work on meteorites. I read recently that maybe only 100 or so people in the world are actually study meteorites full time. Seems a little of a small number to me, but it's not huge, not thousands. Most geologists don't care about space at all. Right? They like things they can touch. Astronomers are very used to not touching anything that they work on, so it wouldn't be good for you, and it's a very long way away anyway. So, what is very rare among asteroid mining people are miners, people who actually know about the mining industry. There are a few people taking some interest in that now, but it's a bit of a strange thing that it's people like me who talk about mining. Here, these things I know nothing about mining, right? Not really. So I think a big influx of those people would help.
Yeah.
Right, but it's a bit of a chicken and egg because until there's sort of a real economic opportunity, it's not worth the miners' time to start looking at. It sounds like a few are now.
Yeah, geologists and miners are used to being recompensed for their efforts, and they wouldn't look at it otherwise. Whereas astronomers, well, we get recompensed, but we're not expecting to make riches out of what we do. So, we don't mind working on abstruse things.
Yeah.
So maybe I have one last question to end things, Eric, unless you have another one from the audience.
Go for it.
Yeah. So assuming that we do start moving out to mine asteroids, for all the reasons you talked about in the beginning, if nothing else, just to make sure they don't eventually hit the Earth. And while we're there, maybe we take some value away. I guess my question is, what do you think? What kind of material are we likely to mine first that's going to make a difference for the future space industry? You can just boil it down.
Whatever makes a profit. If you start I think the big change is if you start making a profit out of space resources, then space will grow exponentially, as we've been talking about, and won't be limited by what the taxpayers are really willing to pay. Right now, we can't expand in space because we are basically still living in the Apollo era of government organized programs. And they just don't grow that way. If once you start making money out of it, costs will come down, the volume of activity will increase, the things you can do in space will increase dramatically, and that will change everything.
I think we're both very much looking forward to that day, and may it arrive sooner than later.
Yeah,
right.
Absolutely.
I'm looking forward to booking a room in your space hotel.
With pleasure, we will help you with that as soon as it's ready.
Okay.
Well, it's been really fun, Martin. Thank you so much for spending some time with us today, and I think we covered a lot of interesting ground. Is there anything else you would like to say as a last word before we sign off here?
This book's pretty good.
Yes.
I'll second that. I've been really enjoying reading it.
Yeah, I've been enjoying it. As
Oh,
well.
yes.
We all have our copies here.
More people sold than I imagined in the whole state.
There we go.
Yeah, we definitely recommend it. It's very interesting and easy to read. Very enjoyable book to read. So you did a great job there. So
Thank you.
I've learned. Yeah.
Excellent. Well, thank you, Martin. And for our listeners, if you have any suggestions for future discussion topics, people that you'd like to reach out and have us interview, or any other comments, just let us know. You can email us at ourfutureinspace@orbitalassembly.com. You can also find us on Twitter at ourfuturespace and Facebook at ourfutureinspace. Thank you so much.
Be well, everyone. See you next time.
Thank you. Bye.